Recording is on.
Do you see that little text window or box? I can't hear you, Michael. No audio, Michael. It looks like your mic is muted according to my screen.
Can I share it?
There.
How's that? How's that, Peter?
Okay, now, when you click on your share, a box opens up and it says share your screen, and in there you're going to click on application window.
Okay.
And then click on the application that you're going to use.
Actually start the application.
Oh yeah, you got to have your application already running in the background.
Doesn't want to show the application window for some reason.
So when you click, okay, so just start PowerPoint, and then come back to Chrome.
And now try it.
Yeah, now click on share your screen. Another box opens up that says share your screen, and in there you'll see a tab for application window.
Ah, there it is. Okay.
And then when you click on your application window, you'll click into your PowerPoint presentation.
Like that. You should see that.
Yeah.
Okay, so I can stop sharing here. Okay, good.
Okay.
Yep.
Good stuff.
Yeah, so I thought about this book for a lot. I've been thinking about it for years and years and years. And finally, I decided to buy it.
Well, nobody in the family could. They always said I was very difficult to buy for it. I suppose so. So several years ago, I decided to put books on my Christmas list. So that's how I built my technical library.
I recently bought the 2020 ARL handbook. I had one from 2010, and I bought the 2020 one with the 6 individual books.
Oh, yes.
And that's pretty nice. Okay, so I'm ready to go.
Okay. All right. Well, good evening, everybody. There's some faces I haven't seen for a long time. Welcome back, Ian. And let's see who else we got here. Al, Cherry, Eric. Oh, Eric isn't going to be around too much tonight. I think he's recording tonight, though. And but apparently he threw us over for cottages or something like that. I don't know why he would do that to us, but anyway. Okay. Well, tonight a bit of a loose agenda. Of course, as usual, if anybody has any questions or problems they wish to discuss, just raise your hand later on, and then we can cover off on that. So tonight, Michael V3TKI is going to present quartz crystal motional parameters SNA comparison with the mini VNA. If time permitting, which I guess I'm sure there will be, I do have a very quick presentation just on a simple RF power calibrator. And with that, I guess we'll get right into that today. I am curious, did anybody attend do any of the viewing of the QSO Today Expo? I watched a couple of the presentations that they had. One was not so hot. The other one was not too bad at all. And I can't remember now what the third one I watched was. Just give a wave of your hand if you did watch any of that stuff. Yeah. Okay. Good. And I know they've got some recordings available for 30 days. They're going to make it up there. And I think there's a couple more I want to watch. Grounding and bonding is probably one I want to watch for sure. Okay. And the new calendar will be ready for uploading very shortly. Well, actually, it's ready to go. I just got to email it off to Peter, and then he'll upload it. And that's the calendar for our schedule for our JITC meetings. Okay. So further ado, I guess, Michael, you're all set to go?
Yeah. Okay. Can you unmute me from your end?
It's funny, I can hear you.
Okay. Well, I'll just hold the space bar down. How's that?
Oh no, you can go to the center of your screen and then just hit the microphone, and then unmute there, and that way it'll stay unmuted.
Yeah. Okay. Got it. Okay. Yep.
Okay, Michael, it's all yours.
Okay, so here we go again. So there's the share application window. Where'd it go? There it is. Okay. So I started out. I bought from actually got from Bob Hudson when the PARC SNA analyzer was built. I decided not to buy it because I didn't think I needed it because I had the mini VNA, and then later on I decided I wanted one. Bob Hudson had built one, so I got it from him. And I've been using the mini VNA, which a bunch of us in the PO Club and the Mississauga Club bought years ago. Not cheap, but pretty effective. You use it with a program on a laptop or a desktop or whatever. So I decided what I would do is try to learn how to use the SNA and with quartz crystals to do the motional parameter analysis thing. So I bought a bunch of crystals from QRP.me, and they sat around for a long time. And then finally, I got myself organized and did it. So what I'm going to talk about is how I did that and compare what I got with what the mini VNA told me. So I change one here. I'll do it this way. Why is it not changing screens? Just a second here. Auto hide ribbon. There we go. Okay. So just a quartz crystal is a piece of piezoelectric material. The quartz is cut into a very thin wafer and bonded with some metallic conductors, films with two conductors, so you can get at it. And the characteristic of quartz is it's crystalline and it's piezoelectric, which means if you put an electric field across the face of the crystal through the electrodes, it deforms the crystal structure. And when that happens, when you deform the crystal structure, that creates an electric field on the terminals as well. So that's how it works, and it oscillates at a fundamental frequency based on the physical size of the wafer. And there's a fundamental frequency, and you can also get it to oscillate on what are called overtones, which are not harmonics directly. They're close, but they're not exactly harmonics. So yeah, so you come to model a crystal in an electric circuit. The crystal is really how it looks. It looks like a series RLC circuit with a resistor, a capacitor, and an inductor in series. And those are called the motional parameters: motional resistance, motional inductance, motional capacitance. And there's also, in the model, there's the lead capacitance between the leads, and you can see that in a diagram at the bottom. And you measure that with an LC meter or the like, and you measure the motional parameters with various different methods, and the SNA uses these to do that. So a quartz crystal actually has it actually shows two resonant points. One is called the series resonant frequency, which is the one where the attenuation is the minimum. And this is a graph of attenuation versus frequency, and you can see the FS at the top left around minus 5 dB or something. That's the series resonant frequency, and that's in the model. The motional capacitance is what dominates that response. And then there's a parallel resonant frequency, usually a few kilohertz higher, where the attenuation is a maximum. And you can see it's way down. Well, it's 90 dB down in this particular diagram, and that's dominated by the C0, like the lead capacitance. And there's a formula approximately relates the two of them, and usually the parallel resonance is a couple of kilohertz above the series resonant frequency. So what I did here, this is a sweep of a 7.040 megahertz crystal using the mini VNA, and You can see the two peaks here, not as pronounced. The lower peak is not as pronounced as that diagram would lead you to believe. But the upper frequency is 7037, 328 megahertz, and the other one is 7049, 794. In other words, 12 kilohertz difference. So it's not the 1 or 2, it's 12, but you get the idea. So there's various ways to get motional parameters. There's a guy, K8Z0A, who wrote a paper on how to do this stuff, an amateur, and he talks about 3 different methods, and if you look in the literature, there's all kinds of other stuff, but one of those methods is to basically put the G3UUR one is to put the crystal, into an oscillator circuit. And what you do is you get it to oscillate, you measure the frequency, and you put a capacitor in series with the crystal, and when you put that capacitor into the circuit, the resonant frequency changes, or when you take it out, it changes. And the difference in the resonant frequency, the frequency shift, allows you to calculate the bandwidth, the crystal bandwidth, which allows you to calculate the motional parameters. There's another method that uses phase shift that looks at the phase shift of the crystal. You sweep the crystal with a signal generator and look at the response, the output, and you look at where the circuit resonates. You can see that, and you look at the phase shift, and you use the phase shift to calculate the motional parameters. The other one, and this is the one that the PARC SNA uses, and it can also be done with the mini VNA, which is what I was interested in trying. Basically, you build you build a simple crystal test fixture which holds the crystal, and it's got an attenuator on either side of the crystal, and you do the test that way. So what you do is you put the crystal in the test fixture, and you sweep it. You've got a signal generator on one side, and you look at the response on the other side of the crystal, and you sweep it over the frequency of interest, and you determine where the attenuation is the minimum, and you determine the resonant frequency, the center frequency, which is the resonant frequency of the crystal. And then you look at the frequency is 3 dB below that resonant frequency and 3 dB above it. And that gets you the information you need. So you take the attenuation and you use that to calculate the motional resistance. And it works because at resonance, the crystal inductance and capacitance are 0 because they match each other rather. So all that's in the circuit is the resistance. And what's in that circuit is the resistance of the crystal plus the motional resistance of the crystal, plus the 2 load resistors, the load resistance on either side, because there's a signal generator and a load on the other side. So you use those to calculate the motional resistance. And then what you do, you've got your bandwidth by looking at the 3 dB points above and below the resonant frequency, and you calculate what's called the loaded Q, which is basically the resonant frequency divided by the frequency difference between the upper and lower 3 dB points, the bandwidth. And having got that, you then go on to calculate the motional inductance with a formula that basically is Q is the formula for Q is inductance divided by resistance. So you can calculate, if you've got the Q and the resistance, you can calculate the inductance. So you go ahead and calculate your motional inductance, and then having done that, you use the resonant frequency formula, which is the frequency is equal to 1/2 pi times the square root of LC. Plug the numbers in to get the motional capacity, manipulate the formula to get the capacitance, and Bob's your uncle. You got the resistance, inductance, and capacitance, and hopefully when you do this right, you get the right numbers. Get reasonable numbers. Not like I did, where I got a minus 5 ohm resistance, and that was because I didn't have a ground in my crystal test fixture. Anyway, this is what the test fixture looks like. It's the The signal generator, or the SNA, one or the other, is connected to it. It presumes, this test fixture presumes that the internal resistance, the source resistance of the SNA is 50 ohms, and the load resistance where you're measuring the output is 50 ohms. So what you've got on either side is a 50 ohm, a 3 dB attenuator, which matches anything on the right hand side. If you look going from the left, it matches anything on the right hand side to 50 ohms. And then you've got a transformer on either side, and what the transformer does is transform the 50 ohms down to 12.5, where the crystal sits in the middle. And that's because the reason for 12.5 ohms, as near as I can figure, is because by convention, crystals are designed to be tested at that, or they're intended to be tested at that resistance or impedance, because it's roughly the same as the magnitude of the emotional resistance. So basically, you got 50 ohms on either side. The crystal sees 12.5 ohms. And in the bottom, this is my my test fixture. It's basically got the SMA connectors on either side. The resistor pad consisting of the 9.5 ohm resistors and 150 on either side, and a toroid transformer, 3743 toroid transformer with 10 turns on either side, set up so it transforms the impedance from 50 down to 12.5. And that perforated board is the same kind of board that that Charlie Morris uses for all his stuff, and it works really well, I find. So that's the fixture. So when you use the SNA, basically there's 3 steps. The first thing you do is you sweep it to get the resonant frequency. Then you, using the filter function, then you sweep it again to get the 3 dB points, and the SNA tells you what that is. And then you narrow the frequency further and you sweep it, and the third sweep you get the motional parameters out of it. And what the SNA does is it knows it's dealing with a 3 dB pad on either side, because that's the way it's designed. So it subtracts the 3 dB. If you look at that test fixture, the loss between both sides, from one side to the other, is the 3 dB attenuation going in, and also one coming out. So you have to subtract the 3 dB times 2 losses from the losses you'd measure, take 6 dB off, and that gets the actual attenuation of the crystal itself. All that's done internally in the SNA. And this is what you get. For example, this is a 7.040 crystal. The resonant frequency measures out at 7.0, well, measured in one test at 7.037.6 megahertz. The 3 dB difference in frequency, which is the 2 outer lines, 220 hertz. So you calculate the Q, and then you can go on and calculate the emotional resistance, 14.54, the inductance, 28.65 millihenry, and the capacitance, 17.83 femtofarads. And from my LC meter, I got the 2.62 picofarad lead capacitance, C0. So you can do the same thing with the mini VNA, only it doesn't do it automatically. So what you do is you start with the VNA and you calibrate it by putting the test fixture into the circuit between the 2 terminals of the mini VNA, and you short the crystal. So the crystal isn't there, there's a short there. You calibrate the VNA that way, and what it does, it assumes is looking, well, it takes the 6 dB out. So now when you put something in the circuit, you're going to get the actual attenuation because the 6 dB is accounted for. So basically, you do much the same thing the SNA does. You sweep the crystal, find the resonant frequency, you measure off the graph that you see the you get the attenuation from the graph, from the sweep. You can see it. You measure the 3 dB points from the graph, 3 dB down on either side of the sweep of the 3 dB points, and then you the resonant frequency, and then you use formulas to calculate the emotional parameters, which is what the SNA does internally. So this is a graph from the mini VNA of my 7.040 megahertz crystal. You can see the minimum attenuation at the top, marker 1, and the resonant frequency 7.037 something. And you can see the 3 dB down points, markers 2 and 3, and that gives you the bandwidth. So then you go ahead and calculate the numbers using the formulas I talked about before. So this is a comparison of 4 different crystals I had doing the test both with the SNA and the mini VNA, and I've highlighted in the middle the results for my 7.040 megahertz crystal, and you can see the resonant frequency according to the SNA is 7.037.6, and the mini VNA 7.037.296, pretty close. To all intents and purposes, the same. It's a couple of kilohertz out from what the marked crystal frequency is supposed to be, and I find that a bit odd. But the intent is that there's manufacturer's tolerances in here, and the intent is that you tune any oscillator you put in it by putting a capacitance in series with it. Anyway, so you get the bandwidths are pretty close, 200 versus 184. The attenuation is pretty close as well, all to all intents and purposes 3.5, 3.6, and the Q values are the loaded Q, I guess is what you look at here. Never mind the unloaded Q. They're pretty close, reasonably close anyway. And then you calculate the motional resistances are pretty close, 11.3 versus 12.4. Motion inductances 28.95 versus 32.43, and the capacitance 17.66 versus 15.77. So to all intents and purposes, it's pretty much the same, and you can use that in those numbers either way. They're pretty close, so I'm quite pleased with that. I just bought a nano VNA, and I was hoping to do the same thing with it that I did with the mini VNA. In other words, set it up and calibrate it with the test fixture shorted, but I'm doing something wrong. I don't have enough comfort with the nano VNA yet to make sure I'm doing it right. So sometime I will, but I'm pretty sure it'll come out the same idea. So what I thought I would do is what I also did, I built an oscillator and checked it out, and I also did an LT Spice simulation to see. So this is a diagram of an oscillator. Just a second. Oh, good. This is a block diagram of an oscillator. Oscillator has a basic amplifier, which is the triangle, and it's got a gain of A. In the open loop gain, which is the gain just straight through, like a common emitter amplifier, just straight through, let's say. There's also an attenuation circuit. The amplifier is an active circuit. It's got a transistor in it. The attenuation circuit is basically passive components, so it's not an active circuit. So you connect it up, so the output of the amplifier gets fed into the attenuator circuit, which is in turn connected back into the input of the amplifier in this, and you can see this in the circuit. So there's a thing called the Nyquist criterion that basically says for a circuit to oscillate, the closed loop gain of the system, which is the open loop amplifier factor A times the attenuation B, A times B has to be greater than or equal to 1. And if it's greater than or equal to 1 and there's no phase shift around the loop, in other words, that attenuation circuit doesn't introduce the phase shift, so you get whatever, there's no phase shift around it, then the circuit will oscillate. And depending on the product AB, you'll either see increased oscillations or constant oscillations or oscillations that die out. Anyway, so that's the circuit, and that means if you have a low gain, like A is small, then B has to be large enough to make the product more than 1, and there has to be no phase shift. So this is a Colpitts oscillator circuit. There's a transistor in the middle, Q1. That's just an NPN transistor, happens to be. The input is the base, where that E2 is, and the output is where E1 is. That's the output. This is an emitter, a common collector transistor or an emitter follower transistor. And the circuit arrangement, the two resistors R1 and R2 are just for bias, and they're large and don't affect anything. So the bottom, so the A is the top. That's the amplifier. And if you had it disconnected from the feedback network, it would give you some kind of gain. And because it's an emitter follower, the gain would be just less than 1. The voltage gain, the collector, the emitter voltage is 0.7 of a volt, roughly below the base voltage. So that means the gain is going to be 0.7 or something like that. So it's just a bit less than 1, which means that the feedback network at the bottom has to have more gain. And let's see, you can see down here, whoops, where'd it go? Sorry. Down here, you can see that the output of the emitter follower goes into the middle of between these, right in the middle of the two capacitors. Capacitors form a voltage divider, which means that this voltage of the output or the top of this circuit is going to be twice what it is on the input. At least twice voltage here at the top is going to be twice the voltage at the junction. So it's got a gain of 2. So you'd expect the A times the slightly less than 1 times 2 gives you a gain of 2 or so. So this should oscillate. And that's the way you look at it. So what I've done here is down the bottom here, there's my amplifier circuit. The feedback network consists of these two capacitors, and this is the crystal here with the series circuits and the parallel capacitor, lead capacitor around it. So this is directly across these here. So that's the feedback network, and sure enough, it oscillates, and you can see it's not particularly clean, which is a characteristic apparently of Colpitts oscillators. It's got to do with what's going on in the transistor, I gather. And you can see down in the LT spice simulation, the frequency here is 7.05 something, close enough to 7.03 or 04. You can play with it by changing the put a capacitor in here to ground if you really want to, but you can see it's oscillating at roughly the right frequency. So I was happy with that. And this voltage is the output voltage right here, right there. So that's the LT spice simulation. You can, oops, where am I here? You can, what I did, I built the circuit on a breadboard, and the capacitors, the black, there's the crystal in the middle. Here, capacitors here, there's the transistor and all the other stuff. And I was quite surprised to find that you don't have to, at least at 7 megahertz, you don't have to build this onto a piece of copper. You look at various YouTube videos, and people have got it soldered into a piece of copper. I didn't want to bother, and I just want to find out if it works, and sure enough, it does. So I was quite pleased with that. It probably wouldn't work very well at 100 megahertz, but it works fine at 7. So then lastly, what I did, I took that oscillator circuit, the one I just showed you, and you can see the, put it on scope, and this is my Signet scope, and you can see the waveform is pretty much the same as what the simulation says. Not particularly nice, but it works. So that's what I've done. I learned a lot by doing it, and shows you can get at these things using a thing like, you can get at these numbers using a the SNA, or you can do it with the mini VNA, and you can get reliable results that you can use to design stuff. So that's what I had to say. There's no more slides, so I'm going to stop here and turn it back.
Okay, thank you, Michael. That's very interesting. I guess we'll go to questions now, but since I'm yakking, maybe I'll ask the first question. Your spice sims, the numbers that it spat out, did it? How close were they to your real world values?
Well, when yeah, my mic's on, isn't it? The real world values were what I actually got was 7.037 megahertz, and the actual breadboard circuit versus 7.05. The simulation shows 7.05. So close, and not exactly accurate, but close enough. And
what about the voltage levels? Did you measure those?
well, the voltage levels are supposed to be 2 to 1, and they were pretty close. Actually, it worked out pretty close.
Oh, good, because I have found that when I've done those kinds of comparisons as you just did there, they get you in the ballpark. And then at least it gives you the idea that you're on the right track. And then if you have to make changes, it also tells you which direction you want to go in. The direction, if you change the value of a capacitor, what way should you go? And you can do that in Spice and see, and it saves you a lot of time on the breadboard.
The other thing is that these results come from a guy called Glenn, who he actually went through the whole theory, all the analysis based on the A times B greater than 1, what that means in terms of the component values, relative component values, and things like that. Mm-hmm. And he showed, he basically did exactly what I did. He put they actually built the circuit. And what he found was that when you use a scope probe to measure the voltage on the crystal, the input voltage on the base of the transistor, it's not the same. The scope loads the crystal, so you got to be careful.
Yeah, whenever we get into some of these kinds of projects, I tell you, it isn't too long before I start getting frustrated and I start blaming my measurement techniques. There's a whole presentation in there on measurement techniques, for sure. Does anybody else have any questions? Oh, while everybody's thinking, I got another one. The motional values that you plugged into LT Spice. The ones you used in LT Spice. You got that from you used the calculated values that you derived from the crystal?
Well, I used both ways. I did it with the particular circuit I showed had the SNA values, the values I got from the SNA test, but the other ones that come out, you get a slightly different frequency.
Right.
If you use the others.
Yeah, that was interesting because when I was looking at when I saw your circuit there, I thought, why didn't you just use a signal source? And then I realized the idea was to take the emotional values and put them in there. I haven't done that yet. That's a pretty cool thing. And I got one more question. Then somebody else can ask. I noticed you had the loaded Q and an unloaded Q for, I guess, the SNA.
The SNA. When you look at the display on the SNA, it gives you a Q. There's a Q that's on the display, and I went and looked at the advanced manual, and there's a whole table of parameters that get displayed, and one of them is the Q, and you can switch between the unloaded Q or the loaded Q by changing internally. I guess you have to reprogram the SNA, and I didn't bother. I looked at it. I saw that was the unloaded Q, and the loaded Q that you get when you calculate it from the SNA numbers and the loaded Q you get from the mini VNA are pretty close. So
yeah,
but the display actually is set up normally, I gather, for the unloaded Q.
Right. Yeah, I remember it generated a fair bit of conversation way back when, but it was so long ago I can't even really remember it now. But and Dave's not here yet. I did get a message from Dave saying he would be joining shortly, and of course the programming of that SNA was his baby, so I'm sure he would have had a comment or two on that.
Yeah, Dave was really helpful in learning about this, and I sent around some results. My initial results showed a negative resistance, and I thought, so I sent it around, and it turned out that I'd missed a ground on the test fixture. So as soon as I fixed that, it was right, and it works pretty well.
That's good. Does anybody else have any questions? Hassan, go ahead. Good evening.
Yeah. When you say unloaded Q, like, does the SNA measure crystals? Because mine doesn't do that.
What the SNA does is if you set it up to measure crystal parameters, you basically start out and you sweep it, and that gets you close to the resonant frequency. Then you sweep it again, and the SNA has a feature to measure the 3 dB points. And then you take those 3 dB points and sweep it a third time with the frequency just higher on the one side and just lower on the other, or just outside the 3 dB points. And you set it up, you put it into crystal test mode, and that's what generates the motional parameters on the screen. That's how you get it.
Was that a separate add-on you had to build, or was it?
No, it's right in.
Oh,
Did
You build the SNA like it's the project from you guys, and does it automatically. You have to build a little test fixture, which basically is those 3 dB pads and a place to stick the crystal in. But otherwise, no, and the toroids. But otherwise, that's all you do, and you just connect it up.
That's
stick the crystal, and away you go.
Hassan, you didn't build the SNA? I can't remember.
I built the SNA. I didn't build that test fixture.
Oh, you need to build the test fixture, because you gotta connect the crystal to the SNA, and it's got to be matched to the SNA input impedance of 50 ohms. So that's why you have to have the test fixture.
Okay.
There's other ways to do it. I think Dave, in the manual, Dave refers to just a 50 ohm test fixture, but I think you have to make some changes to the to reprogram the SNA or something to do that.
Yeah, or the parameters or something like that. So you'd have to do a little bit of a reload.
Yeah.
Any other questions? Well, that was easy.
Yeah, that was easy.
Hey. Okay. Well, thanks very much, Michael. That was very interesting, and it's one of my favorite subjects, actually. It's right high on the list. Crystal filters and all that kind of good stuff. It's unfortunate other projects get in the way, and I haven't been able to delve a little bit deeper into that particular subject. Okay. Well, we had a challenge here, a few weeks ago from one of the local hams here that I took him up on, and that was to build a crystal, crystal's on my brain, an RF power calibrator. So I just threw together a couple of quick slides, and I'll share my screen here and just quickly go through them. Everybody see that?
Yep, no problem.
Okay. Okay, so here's the schematic. The changes that I did was I was given an L387, which is a very low dropout regulator, so we put that in. The original project was a 10 megahertz clock, but the other local ham here, what started all was he had a box of 4 megahertz crystals and found a project to use them up. So that's why we used the 4 megahertz crystal instead of the 10. And the project's based on an article in the QEX magazine, January-February of 2004 by Bob Koksky, K3NHI. I got a couple of screens back to back. If you see the capacitors there, C1 and C2, they're both electrolytics at 1 microfarad in the schematic and the original project, and that's what I built first. And there's my board. The the clock is here, but it's on the underside of the board. When you design a board and whatnot, the time lag between when I designed it and when I actually built it was about 3 weeks, I think. And I forgot that I designed it underneath the board, because when I started to solder things together, and I left the clock to the last one, and then I thought I made a big mistake. It doesn't fit, but then I remembered I designed it to go underside of the board, so the leads didn't have to be jury-rigged. So I guess the answer is to populate a board right after you design it. So over here is, okay, let's go over here first. Over here first is a shot from my spectrum analyzer of the original design using those two 1 microfarad capacitors on either side of that regulator, and I got all this noise, or sorry, all these spurs. This is 4 megahertz here. This here is 3.9 megahertz, and up here is what is it? 4.09. So it's fairly tight. Anyway, I didn't think it was a problem. I just thought it was a bit noisy, but didn't think too much more about it until I talked to the other ham and made some comparisons and realized there was something wrong with mine. Anyway, I went to the application sheet of the regulator and took a look at what they suggested. And so I changed them out to a 0.1 on the input side of the capacitor and 100 microfarads on the output of it. And here was the result. It was really cleaned up. There's the 4 megahertz signal there, and of course the harmonics. Here it is here, all nice and clean. And then over here is when it was with the original capacitors and how noisy it was, or all the spurs up in here was phenomenal. Anyway, cleaned up quite nicely. And here's a little bit of the numbers. The SA, it registered 28.14 after it warmed up for a while. And then the SNA and then it registered, well, basically minus 20. And I have another setup with another AD8307 with a 16-bit ADC in it. And that came in at 20.18, which agrees with the article that was written, and because the way the SNAs, or the 8307s, I should say, read square waves. But my SA, I haven't quite figured out that number, why it's so high at 28. I expected it to be about 5 dB less than what it's reading. So anyway, I threw the numbers in there anyways, even though I don't understand why it's that high. And I'll figure that part out a little bit later.
Is minus 28 high or low?
No, I expected the SA to be reading somewhere about minus 23, in around that area, minus 23, 24 dB, but I'm getting 28.
So that's lower. That minus 28 is lower than minus 23.
Well, so I mixed them up, but I knew which way I meant. I knew what I meant. Thanks.
Yeah. Is it because the SA is showing you just one frequency peak, whereas the other ones are showing the harmonics included?
Yeah, no, it's just that I expected this one to be to be higher than what it actually is. So, and of course I got somebody else to compare with too, because they built the same thing. And of course the article, the article even suggested it comes in around 23 when you're using a spectrum analyzer. So why am I getting roughly 4 to 5 dB difference? But maybe I did something wrong. I'm not too sure in the way I was measuring it, although I don't know how, but you never know. But anyway, something to figure out a little bit later. But regardless of that difference, it's rock solid. After, the power levels, it went from cold was 28.18, minus 28.18. And then after it had been running for, I guess when you're running for an hour, over an hour, it only varied by 0.04 dB. So that was pretty good. And actually, once it's been warmed up for, it'll be well over a half hour anyway. So maybe pushing to an hour, it's rock solid. It just doesn't move.
Hey, Peter.
Yeah.
Going to come back to what Hassan was asking. The SA, is that the fundamental you're reading?
Yes.
Okay. And the SNA, you're just plugged it in, you're seeing everything. There's about a 10 dB difference in readings there, right? So the SA is not counting the harmonics, and I believe the SNA is. There's a calculation. If you look in that Bob Kopsky article, there is a calculation he does to compensate for all of the harmonics.
Yeah, I looked at that, David. I'm going to have another read on it again. Maybe I misread something, but I'm sure he calculated, when he did his calculations, he came in at minus 23. Where, so his other ones, like his 8307 readings were, roughly the minus 20, but his SA read about minus 23, and here I'm at 28. So
right, but you can't expect to get the exact same readings he have, because when was that article published?
2004.
Yeah, so that was 16 years ago.
Now,
So,
now the only thing I can say about that is, you know Dave, EAC, here in Kingston. Well, he got 23. So something's not quite right. But even if I never figure it out, I'm still happy with it because it's rock solid. The frequency shifted from cold to warmed up about 10 hertz. And after, again, the same thing after well over a half hour anyways, 45 minutes or something like that, maybe. The frequency never budged. It stayed at 3.99947 megahertz. So that was pretty good. Anyway, that's what we've been up to this past week or so. Yeah, just okay, we're back. So, Dave, you missed your favorite subject, SNAs and crystal parameters. All right. Does anybody have any questions about anything so far tonight? No.
I had a question. So if you put some ferrite beads between the power rail and your CMOS oscillator, that might fix it or just boost the capacitance a bit more. I'm just guessing, but that might be
more than 100 microfarads.
I mean, you might need I don't know. Was that electrolytic cap or was it ceramic?
Yeah, I was actually thinking of going less to see what happens.
Well, first of all, you need tantalum caps right at the chip, because electrolytics are for bulk storage. They're not for high frequency transients.
Okay.
So if you're not getting enough drive strength, that might explain why your number's so low. So you stick a tantalum, just stick tantalum caps right at the power leads, and maybe a ferrite bead or two to block any other RF, although that might not be necessary. That could do it, solve it.
and you're also
What's the difference between the electrolytic and the tantalum then?
I think the electrolytic is high power, but at high frequencies it doesn't deliver as much. Whereas tantalum, I think, will deliver a surge of current at a high frequency, like instantly. The electrolytic will deliver a large current, but it takes too long. Like if it takes a millisecond to deliver the current, for RF it's useless because
Well, that's interesting to say, because look at the results I had when I used originally the 1 microfarad capacitor and on all the crap that was being generated. And then the 100 seemed to clean that way up. Now my first reaction was, okay, maybe I can go lower and maybe that might improve things as well. But I'll try your suggestion on that one, Hassan. Thank you. And fellow Gister would like to speak. I guess that's Dave.
Yeah, no, Peter, what I was going to say was that what you're supposed to also do too is, I can't remember what the rationale is. W2AEW talks about it. Dave Jones talks about it, is that you have to put multiple capacitors, because I think it has to do with the self-resonance or ESR or something like that.
Mm-hmm.
So you put like a 10 nano, 100 nano, and then a 1 micro, right? And you put 3 capacitors, and what that does, that's better than putting one, like say 2 microfarad. Put 2 1 microfarad capacitors, or 1 a microfarad, and then I don't think you can get a half a microfarad, but a half a microfarad.
If you put them in series.
That has to do with.
But if you layer them, you put multiple capacitors in parallel, then it reduces more noise.
What I thought that was about was making the different capacitor sizes resonated have different values of impedance at the particular frequency. So you ground the particular spurious frequencies with the different capacitors.
That's correct. Yeah, that's correct. So in essence, by you doing that, you're getting a cleaner rail.
Yeah.
Actually, that's correct. That's actually correct. You would have, if you're trying, your power rail, the transmission, the line on the PCB trace has a certain inductance. And so if you just put capacitors and then you got an inductance there, at certain frequencies, you'll get this resonance. But I don't think that's true at 4 megahertz. I think it's probably at 100 megahertz or more. At Intel, for the FPGAs, we had this design tool which told the customers, for if their FPGAs at this frequency, what caps they need. And the tool would recommend 400 capacitors on the board. And customers just laughed at it, saying, something's wrong here. And our competition only had 10 capacitors. So they retired the tool.
You got fired?
No, they couldn't find anyone to take ownership.
Oh,
but I think I recently read a different theory of how this is supposed to happen. I can't remember where I read it or what they said, but there is a different way of looking at the problem. But you guys are correct. That does happen. But I think if you calculate the inductance of your traces and the cap values, you'll see that the resonant frequency is probably more than 4 megahertz. I think that the solution is just put the caps as close to the IC as you can to your CMOS load, your 4 megahertz oscillator, and that just takes care of everything.
okay, so not close to the regulator itself then.
Well, you can put them in both places, I think.
Well, I'll mess with that and see what happens. That certainly is an interesting theory and worth trying. I think I have some tantalum caps, so we'll find out. Kevin.
No, sorry. Okay, you can hear me? Just
yeah.
I haven't talked spot yet. Anyway, there was a podcast this week. Ham Radio Workbench had a guy on. They talked about RF measuring instruments and all this kind of stuff, and he actually was talking about that exact thing about decoupling caps and reducing phase noise, and they go to great extents to keep the rails clean, and it helps a lot with everything. And that's exactly what he's saying. You can't have too many decoupling caps. Maybe not 100, but more than one. So anyway, but that was a really interesting podcast. It's about an hour and 3/4 long, but it was very entertaining. And the guy he's like 76 years old. He's been around forever, and he knows, and he talks about everything from microwaves to HF. It was really interesting. Anyway, that was my 2 cents.
Did you send a link?
Okay, yeah, I'll put up a link on the group.
Yeah, I'm gonna share my screen for a second here. Can you guys see this?
Yep.
There it is, W2AEW. In this video, he talks about why you need multiple caps, and I'm pretty sure in it, he goes through and he shows you, he does some calculations in here. But anyway, take a look at it. That's the video I was referring to. And I'm pretty sure, here's the other one by Dave Jones. I think Dave Jones also has one too, where he talks about multiple bypass caps. They're both very good videos.
Well, it was certainly interesting when I saw the change going from that 1 microfarad capacitor up to 100 and the difference. I never would have expected that kind of difference, but proof's in the pudding, isn't it? Okay, anybody else have anything to say?
I have one question, Peter.
Yeah, go ahead, Cherry.
So you were mentioning about some QSL Expo which was going on in the beginning of the call. QSL Expo something. What was that about?
I didn't quite catch that. I mentioned something at the beginning. QSO today?
Yeah, something like that. Yeah.
Oh, yeah, QSO today. Was it 2 weekends ago or last weekend? They had an expo, an online expo on Saturday, Sunday, and they had a ton of seminars that will be available for the next 30 days. Well, won't be 30 days now, but ready for another 2 weeks. So if you're interested in it, just Google QSO today expo, and then just register, and the videos would be available for you. I think there's be about another 2 weeks before I guess they'll take it down.
Okay. Okay. Thanks. And just one question to anyone, like, did you guys go to that recent Hamfest last week? I am not sure whether it was there. It was in Hanover.
Yeah, I didn't go, but one of the local hams here did, and he said they did it. It was very well done and had a good time. But
Wow.
then again, this guy is a Hamfest junkie, and he goes to all the Hamfests around the world. So
Okay.
yeah, it looked like it was a good day. It was a nice sunny warm day, and the pictures certainly looked like everybody was having a good time.
Yeah. Okay. I'll search for the pictures. So I usually try to go to all the Hamfests in Ontario, and this. I wanted to go and I missed it. Yeah.
That'll be a while yet, I think, but we'll see. Okay, anybody else have comments, questions? No, Frank, had nothing to say about the direct conversion receiver? Where'd he go?
Just unmute myself there. No, I haven't done much work on it at all, mainly because I'm still cleaning up the basement. So that's taken most of my time. But I do have a couple of comments, and one is I really enjoyed Michael's presentation this evening. So it was very well done, Michael. And if you happen to miss the QSO today, there's another similar type online convention coming up on Saturday, September the 5th and Sunday, September the 6th, which is put on by the English GQRP Club. And it's much the same type of presentation. In fact, a couple of the same presenters will be there as what was in the QSO today, namely Hans Summers will do a presentation. And there's also one on HF propagation and QRP, homebrewing, single sideband transceivers, and of note, one on the vector network analyzer and the nano VNA, which should be worth watching. So it might be something worthwhile to look into and register for. The difference is I think there's a £4 English cost for it, which turns out to be about $6 along that line. So I've registered for it, and if I remember it, what happened with the QSO today was I completely forgot about it. I missed the whole thing. And one more thing, talking about SNAs and the like, is I still have available one of the PARC SNAs, completely built and tested and everything. It just needs the labels put on the case, put in the case. And if you want it, it's $50, which is less than half the price that we paid for them for the build-a-thon. So, and get a hold of me, probably both. If you don't know the email, then call to Peter or Dave or any one of those guys. Know what the email is. So back to you then, Peter.
Okay, thanks, Frank.
I have a question.
Yeah, go ahead, Michael.
Or comment regarding the Nano VNA. Al Walkie did a presentation to, I think it was the Denby Amateur Radio Society in England, and it's a two-part thing. The first part talks about 3 dB intercepts, no, third order intercepts, but the second part is all about the Nano VNA. And on that basis, I bought one, and I bought it from the company that he referred to. I actually emailed him and asked him where he got his, and he got an H4 from a company called A&L Electronics in in the US, so I got mine there. But he's pretty good. He has a pretty good explanation of VNAs and the nano VNA itself. And there's also another guy, Joe, somebody that has a 56-minute presentation on the nano VNA as well. My other question is, what about these presentations? Is it worth thinking about uploading the presentation somewhere? Like, I presume.
You know, when you were doing your presentation, Michael, I was thinking there's a lot of good information in there, and I was just thinking that very thing. We should maybe make a spot in the we can make the spot in the homebrew section on the website, and maybe we can upload some of our presentations there instead of Groups.io, because Groups.io has a fairly tight limit on space. So, and that we were sharing with the other group. So the website, I believe, has tons of room. So I could talk to Peter about that, and we can make another section in there, and we can upload our presentations there.
Just a thought, because some of it's valuable and more interesting than mine, perhaps, but to upload it and have it for other people to look at, you know.
Yeah, Dave, comment.
Yeah, why don't you just use YouTube? Because we could stream Jitsi directly to YouTube. That's one option. Or you could record it and then load it onto YouTube. All we have to do is create a PARC YouTube channel.
Well, when Eric gets back, we can sit down and talk to Eric, because he's recorded all of our Jitsi meetings.
Well,
So-
isn't he? He's on this call.
Well, he sort of is. He's doing cottage stuff, but he's recording He's recording anyway.
Oh, okay.
So I forget where he's got. He sends a link out every once in a while, but we can talk more I'll talk to Eric a little bit more about that. But I suppose that's it. But if somebody wants to have the actual presentation itself, you know.
Yeah, I think the issue was that Joe created a YouTube channel for us, and we couldn't get the password for it or the link to go to it. I say, you know what, just create another channel.
Yeah, well, Derek's already done something, so let's talk to Eric when he gets back. I'll talk to him this week and just see what's going on, where it can be a little bit more accessible. But if we want to upload just the, say, straight PowerPoint presentations, where will we do that? We could make a spot on the website.
A PowerPoint presentation, you could create a PPTS and
That's right.
create it into a video, and that could be uploaded as well. Or you could those static type files, put them on Groups.io or wherever. They're small. They're not a big deal. But like for videos, I would put YouTube, because that's what YouTube's for.
Yeah.
And you can even make them private, so that only certain people can go in and view them if you want.
Mm-hmm. Well, that's two different subjects. The one's the video one, and the other one, what do we do with those? The ones that Eric is recording. And then the other one is, if we have in these presentations, there's lots of good information in there. What do we do with them? And I'm thinking, put the actual presentation itself, the PowerPoint presentation, as you suggest, turn it into one of those self-viewing ones, and upload that to the website. Okay. Any other comments, questions from anybody? All right. Oh, I guess that's about it then. Nobody else working on any interesting projects? Oh, wait. I got some nice new toy.
Yeah, I got something new.
What would you get?
Oh, so I think it was Dwayne who told me about that $12 logic analyzer. So I picked one up, and that thing is amazing. Here, I'll show it. I'll turn on my video. Tell me if you can see it. It might take a second, but I hooked it up, and the software is called PulseView, and it worked right off the bat. And you know, I've never had that experience in a long time. Where it actually, can you guys see it? So this is the logic analyzer. You see this here?
Yeah.
There's no company name. It just says analyzer, but they're all kind of knockoffs of something. This is the software. You can kind of have it hooked up to this board here, which is just was blinking, and here's the LED, for example. That's the blink signal. And I was doing some stuff like just checking out the trace features, so that's a bit advanced. But you can see here when I did a reset, it kind of did some stuff and then turned on again. And this thing is amazing. Like for $12, it actually, you can see all kinds of things. I mean, we could have debugged that encoder problem that we had with one of the boards. You can debug UARTs, serial port problems. So yeah, I highly recommend everyone get this. And thanks for recommending
it up from?
What was that?
Where did you get that from? The logic emulator?
I got it from Banggood, I think.
How much memory does it have?
How
much- Like
I don't think it has very much.
how much data can it capture? Because a lot of those devices only capture a limited amount of data.
It stores to the PC.
So what's the maximum frequency it can it decode like a 10 megahertz signal and feed that to your PC?
Yes.
Mine says 24 megahertz.
Yep.
So and that's going across USB?
Yeah, USB. Although they say that to get it to work over USB, you need perfect conditions at 24 megahertz. So
Yeah,
you might have to
because-
go down to 16.
Yeah, and if you're capturing, how many lines does it capture?
8.
8. So if you're capturing 8 lines and they're running at multi megahertz, does USB have the bandwidth?
Barely.
That's why the other ones, they've got memory and it takes a snapshot, then it feeds it to your PC.
Yeah, it's kind of pushing the limits. So this will be 24 megabytes per second, and USB is like 42 megabytes per second. USB 2. But they say you should get a high quality cable, maybe not the one that comes with this thing. And the second thing is, the GUI says that you can store up to 1 terabytes of samples. So it's basically limited by your PC memory. So I don't know how much buffering they have on board this thing, but for $12, I mean, it's pretty good for just kind of debugging Arduinos and stuff.
Maybe you have to do a demo one day there, ask that.
Yeah.
Okay. And Dwayne, I see you have a new toy to play with.
Yes, I do. This is the little tiny SA. I picked up one of the first production run on it. Right now I've got it setting up with just the little whip antenna that comes with it, and this is the local FM band for $50. It's an amazing piece of equipment. It's got a 0 to 100 kilohertz to 350 megahertz primary input frequency response, where it goes through filtering, and it's got a built-in attenuator. And you can also go and look at the full bandwidth of 240 to 960 megahertz, unfiltered, unattenuated. That's just raw input to the local oscillator first IF. But I've been playing around it for about a week or two now, and it's an amazing piece of equipment.
But they seem to be cramming a lot of stuff into on a $50. That the mini VNA, now an SA. I don't know. Dave, maybe we bought our SAs too soon.
That's okay. I'm happy with my essay. That's a real essay. It works, and I know I can trust it. But I think that's a really cool device. I think for the price, Dwayne, I think that's an excellent device for your bench. And I think if you don't have a proper SA, why wouldn't you use something like that for like $50?
Oh, for sure.
Yeah, like I think that's a really good find.
Yeah, it has a lot of features in it that I haven't seen on some of the a lot more expensive ones. I did some stuff on my blog about it, and has got a harmonic function in there. You give it the fundamental, it goes and gives you the first three harmonics. It gives you the attenuation and the actual frequency offset from your fundamental.
It'll be interesting to see how you make out with your add-on there with the tracking generator.
Yeah, I ordered some boards the other day. Hopefully I'll get them in a week or so. It's going to be basically very simple. They bring out the LO, and all I need is a mixer and a 433 meg oscillator and a low pass filter to bring it down to the right frequency to get rid of the upper harmonics.
Great. Okay. Anybody else have any new toys?
I had a question. Someone told me about this radio called an SDR called the Xiegu G90. I was wondering if you guys had heard about it, and what do you think?
I've read some stuff off and on, and I can't remember where I've read about it. It was probably on one of the Group IO's ones that I have, but I don't really recall much about it, Hassan, so I can't make a comment in that regard. But other than to check maybe on Groups IO, they may even have something going on Facebook pages as well with SDR stuff. But I think it was probably in the Groups IO somewhere.
I've got one of the small Xiegu, the GN1, I believe it is. It's a small, really small 4-band. It's about half the price of the 90. And it worked quite well.
I have a question, an unrelated question.
Yeah, go ahead, Michael.
When I was a kid, I built a Lafayette KT-135 regenerative receiver, and I gave it away, but I've been given one, and it needs new filter caps because it's humming. And the filter caps, it's in the schematic, are 30 microfarad, 330 microfarad capacitors. As far as I can tell, there's nothing wrong with, like, you can get 33s, but you don't seem to be able to get 30s. I wouldn't think that's a big deal, right?
I don't think so.
Yeah, that's what I thought. So I'm gonna do what I can with it. Yeah, okay.
Yeah, I mean, in theory, infinite caps are the best for filtering.
Sorry, which caps?
Like the higher, the better.
Yeah, okay. So 33s should be fine then, as long as you pay attention to the voltage, right? Okay, thanks.
Yeah.
Great. Okay. I guess last call. Any comments, questions? Hearing none, I guess we'll say.
Well, hang on. I got a question. Has anyone played around with antennas for a restricted yard? Has anyone put up any antennas in a small backyard where you're not able to put up a dipole, where you can't put up a proper antenna?
Don't buy that house. Are you crazy? You're getting tired. You buy a place where you can't put up an antenna? What's the matter with you?
It's too late. It's called being married.
Well, you can cure that.
Well, I have a mini quad from Tom McKay in Stratford. It's a 3-element beam, and it works quite well. It's not huge, but it works for me.
No, I can't put anything on top of the roof.
I use a G7 FEK, which is only 28 feet high and 50 feet long, and covers all the HF bands.
What's that, Dwayne? Say that again.
A G7 FEK is basically a pair of back-to-back inverted Ls. Total height is about 28 feet, and total length is about 50 feet.
Yeah, okay, I'm seeing video. Oh, it's fed with a ladder line. So it's kind of like an off-center fed dipole.
You really don't need ladder line. That's just the way they're built. You can just go and put about a 6-inch insulator up on the top and just go straight up with a piece of wire on each side. That's just, ladder line is just the easiest way to keep the spacing between the two elements.
Yeah, it says 51, and is it? Oh, that's the Wyndham. half-size G5 RV. 6 bands, including 80 meters.
So did you buy that joint then?
What?
Did you buy that place that you shouldn't be buying?
I already did.
Oh,
No, because what I was looking at is I was looking at like a random wire, because I can string a random wire around the roof of the house and just put grounding radials in, right? Use like the gas line coming in and use other radials, put a few radials in, and then just have a random wire on the roof and load it up. It doesn't radiate as well as a dipole, but you're going to get out. The other thing is putting one of those verticals in that you put, those, it's basically, Peter, like, remember I was asking you about that vertical that doesn't need radials? It's basically an end-fed antenna, and you're supposed to put radials in. Doesn't matter what you'll get it'll work a lot better if you put radials.
right. Huh. Well, I guess you're going to become the expert then. What did you buy? What kind are you buying?
Yeah, Ian, go ahead.
I've got a pair of these hamsticks.
You're cutting out, Ian.
Oh, okay. I got a pair of these like Hustler hamsticks. Get them from
Oh, yeah.
Vans. And it's a J.
What are they? What's those ham sticks? What frequency are they on?
So you can get them for different ones. I've got 40 and 20 right now. Get them. I just mount up to this. I had some aluminum extrusions with bolts on them. So I had 40 and 20 and had room for about 5 different bands I could put on there. And I just had it mounted on the balcony.
Okay, because I did experiment a few summers ago with just a ham stick dipole, just a regular ham stick, and it worked. But I found the bandwidth was very, very narrow. Had a very, very narrow bandwidth.
Yeah,
I need the tuner to work it.
Yeah,
But the tuner was pretty good.
Yeah,
I confirm that. I have a ham stick pair for 30 meters, and it works, but it's very narrow.
Yeah. Do you use a tuner, Michael?
It depends. It's 30 meters. My MP seems to be able to do it. The resonant frequency is about 10-150 or so, or 10-140 or something, but the MP tuner is capable of doing it. But I do have an external tuner that I would use if I had to.
Does it work well?
Yeah, it's okay. I get out to Europe, it works.
Okay. How about Ian? Did you find yours works well, or you haven't built it yet?
No, I had it up in my old apartment. I didn't put anything up here at the new place. But it did the job getting into South America.
Al, you had a comment?
I did. Am I getting out? Okay.
Yep.
Yeah. I've seen a dipole made with 2 screwdriver antennas back to back. It's directional and fully adjustable. You might want to give that a try.
You mean the screwdriver antennas you put on like a car?
Yeah, 2 of those horizontally back to back, and put it on a mast, maybe with a rotator. I don't know how good it would be, but it's fully adjustable.
Are those?
That's basically what these are. These are car antennas back to back.
But they don't.
Adjustable ones.
With the screwdriver antennas, you could tune them for different frequencies, right?
Yeah, you can.
Is it an auto tune, or you have to make? I remember. I know the concept, but is it you have to go and manually tune it, or is it something it automatically tunes?
No, it has a little motor in them where it screws in and out to change the resonant frequency.
But it's not. It doesn't do it. It doesn't do it automatically. You have to move it yourself.
No, yeah, you move a button, push a button.
Okay.
I think there are some controllers where you can actually set the frequency after you've tuned it, and you can just hit the button, and it'll go to basically a certain waypoint or adjustment.
We used to have a ham in the club that used to make those antennas. I can't remember his name now, but we used to make these screwdriver antennas. I was up visiting one time, and he had quite a shop set up there just to make these antennas.
Is
Yeah,
Gunther Schwegel?
Pardon me?
Cheap.
Is
They're
it
not-
Gunther Schwegel?
No.
The MFJ antenna is $270 each to get one screwdriver antenna. It's not cheap.
Yeah, it's a little cheaper to go my way. Sure,
Well, since you probably got lots of money anyways, Dave, because you didn't buy a house with a big backyard.
No, I can listen, man. I can buy a random wire tuner, like a ICOM tuner, which will tune anything from like 8 ohms up to 6,000 ohms, right? And it's $400.
Yeah, that's
So
what I
that's-
use.
What's that? Yeah, and so I'm thinking for like $400, I get that, and I can basically tune any band. All I got to do is get a proper length wire, get it up as high as possible, and Bob's your uncle. And you could even use that to tune a vertical as well, too.
Yeah, I think buy a good tuner. It sounds like you're going to need it.
Yeah.
Yeah, you got no space.
Maybe it's time to put
Just
up
had a thought.
goal.
Okay. Any other comments, questions?
Yeah, I just had a thought. If you have, so right now, usually you drive the antenna from the middle and you rely on the length of it to resonate. But if you put 4 amplifiers, or one amplifier in the middle and then 2 on the ends, and adjust the phase, you can use any length of wire to resonate. You just have to drive it in such a way and adjust the phase manually. Then any length of wire would work. So we should try that out.
Well, mock one up on your bench. And then you can let
Yeah, I'll try to get this.
Dave can leverage that design for his roof. Right, Dave?
Yeah, well, I've got my R5. I can put up, that's just a vertical. All I got to do is put a mast, and I can put my R5 up. But that's 20 and above, right? 5 bands, 20 and above.
Yeah, I've got an R5 as well. Yeah.
And I won't get 80 or
No, you won't.
on that.
You know what? I have transmitted on 40 meters on mine. Doesn't go well per se, but you can get out. You won't work all countries, maybe, but
Yeah, because I think for the kind of stuff, Peter, that we'll be doing, like 40 and 80 is probably what we'll be using most of. 20 is great. 20 and above is great if you want to get into doing DX or contesting, right?
put your R5 up and then just figure out something for the 40-80 or at least 40 anyways.
Yeah, and that's what I'm thinking about the random wire.
Or even something you can load up and where you can do 40, 60, and 80.
Yeah.
And that's what I've done with my Wyndham out in the back there. That's the one I used for the 40, 60, 80.
That's what I used to have before. I used to have an off-center fed dipole, and I used to load that up on 40 and 80, and it worked well.
Yeah. And then just put your R5 up for the other stuff.
Yeah, but I can't put the Wyndham up. I can't put that off-center fed dipole up. I don't have the space for it. I'd have to go across to a tree yard.
Well, make a zigzag out of it, whatever, just to get it up there somehow.
So I'll find something else. I'll figure something out.
Make it a bit of a V shape, and it'll give it a little bit of in the appropriate spot, and you'll give it a little bit of directionality to it.
I've even gone rogue and looking at the eaves trough, walking around the house and going, "Ooh, I could load up this eaves trough."
Interesting enough, my G5RB came down in the last storm about 3 weeks ago, and it's laying on top of the roof, and it still matches. I'm still getting out, and it's still better than my other antennas that are still up in the air. So maybe you just lay it on top of the roof.
Yeah, well, that's what I was going to do. Was just the other thing too. We've got an attic on either side of the house. It's not on top of the house, and I was even thinking of just putting wrap around the dipole around, and just seeing if it would work. Put a dipole, because I've heard people saying to take dipoles and just they don't have to be straight. You can have them twisty and bending and coiled, and they'll still work. They won't work as great.
What about pulling up a? When I first started, I have a semi, and my first antenna was a G5, a shortened G5 RV. But the back of the house, the yard is 30 feet wide, so I attached the ends to either side of the fence and just pulled it up over the roof. So the peak of the antenna, the apex, was about 6 inches off the roof, but it worked. And also, there's a guy in our club, I used to be in our club, who claimed he could load up his furnace ducting. And it worked.
Well, I think, you know what I was reading, if you look at some of the tuners, they actually have a section about loading your eaves trough. They actually have a section, and they talks about loading up your eaves trough. And they said it'll work provided it's not full of water or snow, because they said once it's full of water or snow, it's not going to work. And they said it's possible to do it, but you got to have radials. As long as you've got radials, you can get that, you could make it work. It may not work great, but you'll be able to get something being sent out.
Okay. So where did you buy it? What town are you going to be located in then?
Paris.
I passed through there once. Okay.
Well, it's better than Kingston.
Oh, I don't know about that. I do know that. I'd rather be in Kingston than Paris.
You got an ex-penitentiary out there, and you got a bunch of military guys running around.
Safest city in town. Safest city in the country.
In my direction.
Paris is safe too. There's nobody there.
Yeah. Well. Okay. I guess that might be about it, unless there's any last-minute comments. Everybody?
Just a comment for Dave there. What you can do is just try any type of wire antenna and use Whisper, and it'll tell you exactly how the antenna works compared with other antennas. So you put it up and check it out, throw another one up and check it out with Whisper, and you can tell what the best antenna is.
Yeah, that's kind of what I was going to do, Frank. Not really Whisper, but just get some kind of wire up and just try and load it up and see how well it works.
You know, that's a good idea, Frank, because there's around Kingston town here, there's about 3 or 4 hams that have been playing a lot with Whisper and just doing that. A couple of them just moved houses as well. So they were able to do checks on what the old location was like and then what the new setup was like. So the Whisper mode has been pretty popular around town here in the last several months. So that's a good idea.
It tells you your directivity too, with regard to the antenna.
Yeah. We need more stations in Canada that are actively listening for Whisper too, really. But what can you do?
Yeah, if you want to try those hamsters, I'm using mine right now. It moves. You can only be half an hour away from me. I'm home with it for a while.
Yeah.
If you want to try them out before you buy.
The other thing that's on my mind is 2 meters. I'm thinking, oh, is there repeaters around here? Is there?
Oh yeah.
There?
There's repeaters out this way.
No, where at? Ian?
I'm in Guelph now.
Oh, you're in Guelph. Yeah, I don't know if Paris or Brantford has any repeaters. It'd be great if the repeater had IRLP or something which I can connect up to other repeaters.
Yeah, because we certainly know one place that doesn't have IRLP.
Yeah. Ooh.
Okay, maybe on that note. Okay, guys. Thanks for joining tonight's session. Great seeing you all again, and I'll put the schedule for the next for the rest of the year for our Jitsi sessions. Right now the schedule is going to be our more casual one, for lack of a better way to coin it, will be the first Wednesdays of the month, and then of course this one on the third Wednesday, and that pattern will be repeated for the rest of the year. So it'll be 2 sessions a month. Okay, well, thanks again, everybody, and see you next time. 7-3 from Peter. P3.
Thank you, Peter, for hosting.
You're welcome. Thanks.
Bye.
Okay, bye.
See you around.
See everyone.
As you notice, Peter, I finally logged in.
What was the problem?
Well, I was on the main org site, and they don't have a quick link to meetings.
Oh, was yours the problem? Oh, from your end. Ah, okay.
Yeah, logging in the wrong place.
Yeah, I was just wondering because when you said I was worried for a minute there when you said you had trouble logging in because you know there shouldn't be a limit on anybody coming in, and yet you're having a problem. And I thought, geez, and I knew there was about 3 guys sent me messages saying they couldn't make it out tonight for one reason or another. And but anyway, well, glad to see you back out again, Simon.
Yeah, so now I'm officially a developer, apparently.
A developer for what?
For Jitsu.
Oh, you are you? Okay. Fair. Well, then I'll send you some ideas for improvements.
Okay. I'll catch you next time. Thanks.
Yeah. Cheers.